So, in the last class we have introduced what is called a fundamental solution. Fundamental solution phi. This has a singularity and you have seen that Laplacian of x phi equal to 0 in Rn minus 0. And then we also introduce what is called a convolution. I did not give anything about whether convolution is meaningful, but formally we introduced a function ux equal to phi star of f. That is nothing but integral of phi of x minus y f of y dy. Then we are trying to do something, we are trying to differentiate u with respect to x 2 times and sum it. To do this one you take du by dxi, and again the question is that the question we have asked, even if the convolution is meaningful, can you do the differentiation Laplacian of x phi of x minus y f of y dy. But this is not correct, not true. The problem is, to do such things you need what is called a local integrability. So, I am going to discuss something, local integrability. So, phi I will this will give it as an exercise, but we will explain to you something. Phi, grade phi are locally integrable, but the Laplacian of phi or d square phi by dx, the second derivative is not locally integrable. So, what is the meaning of local integrability? So, let me, all of you know it, but saying f is, or g, let me put g, is locally integrable if integral of mod g is finite for all compact k. Okay. So, I want to discuss something now interesting. So, I want to, if you look at it, phi has singularity of the form, except n equal to 2, you have singularity of the form 1 by mod x a power n minus 2. So, this is the singularity type. So, the singularity is at the origin and at the origin at 0. So, you have to see the local integrability in a neighborhood of 0. So, basically you want to understand, so wish to understand this one, wish to understand integral over a ball of radius in a neighborhood of 0, any neighborhood. So, let me take a ball of radius 0, b1 0 is 1 by mod x power alpha, when is finite, when, this is the question, where b1 0 is the ball of radius, which you know it is an open ball of radius x in Rn. More generally Br of 0 x in Rn such that mod x less than Br. This is the ball of radius R. This is the ball of centered at the origin. So, similarly you can define what is Br of any point x naught. It is the ball of radius x in Rn such that mod x minus x naught less than R, and its boundary you can have it boundary of ball of radius 0 is this is also SR of 0 if you want the surface is which you already set of all x in Rn and such that mod x equal to R, you see. So, you since the singularity of 1 by mod x power is at the origin, it is enough to check near the origin. In other point there is no need to check because the function is smooth and C infinity, you do not have to worry about it. So, only you have to see when this is. So, what about when n equal to 1? This you know it, n equal to 1 it is 0 to 1 by x power alpha. You know that this is familiar to you, this is infinity if and only if when alpha less than 1. Of course, when alpha is negative no problem because then there is no singularity, it goes up. Only when alpha equal to 1 also there is no 0 there is no singularity, singularity comes only when alpha greater than 0. So, you have to check only the singularity at that point. Okay. So, I want to also tell you few more things because we will be using it frequently. So, if you integrate without that 1 by mod x power alpha on a ball of radius 0 dx, this is nothing but its volume of the ball of radius, right, volume of B1. Okay. So, that is there are different notations, you write it as volume. This you have a precise value, you can refer some books. Yeah. This is also a notation, we call it is the volume of the unit ball, volume of the unit ball, okay, in Rn, unit ball in Rn. You can actually, what I want to tell you here few things, how do you make some change of variable. If you have a ball of radius r 0 with dx, you can make a change of variable x is equal to, what do you want to put it? So, you want to write it x is equal to you make a change of variable x is equal to make a change of variable x is equal to r y. So, when x varies from 0 to r, y varies from 0 to y, but then dx will become r power n. So, this is r power n with the ball of radius 0. So, all this should be familiar, okay. dy, that is nothing but r power n omega n, the ball of radius. So, it is better to know all these things, ball of radius. Similarly, you have a surface area. If you have a surface, you are integrating, you have learned now the surface measure. So, if you have d of B1 of 0, so you have your differentiating, integrating, not differentiating with respect to the surface measure on the unit. So, I just mentioned ds1, this is with respect to y, this is nothing but the surface area of the surface B1 of 0, and you can show that this is nothing but actually you can prove it. I will come to that, maybe I will give a proof of that. Okay, you can see that one. And when you do, for these are all formula you have to be familiar. dBr of 0, how do you make these things? Of ds, this is a surface measure on the surface of radius r of y, dy, not dy, there is no dy, we already put ds. Okay. So, you already have ds of y. In this case, you got r n omega n, here you will get r power n minus 1. So, you because you are only integrating with respect to the surface, and surface has the of a n minus 1 dimensional object. So, you will get only, you can see that the surface elements on ds ball of radius r is r power n minus 1 of surface measure of n of y of dB1 of 0. So, this is nothing but r power n minus 1 the surface measure. So, the surface measure of ball of radius r is this r power n minus 1 into surface measure of ball of radius r. Okay. And this we are already telling that how do you do that part. So, this is this formula, this is nothing but the surface area of the ball of radius. Okay. By shifting it will not change. So, let me give you how do you do this part. So, let us compute. So, the proof of this let me give you quickly, because this will be using it again and again. So, let me use it in a different color. So, you have your B1 of 0 dx, this is your volume of the unit ball. That is what I am saying, the surface area is n into the surface area of the ball of radius 1 is n into the volume of that one. So, this you use Fibini. Here I want you to come in, this is nothing but 0 to 1 dr integral the ball of radius r of 0 dsr of y. That is natural. So, what you do is that if you have a surface and you want to understand the whole volume, so you understand the surface area, all the surface area and integrate. This is typically the Fibini theorem. That is what you do it. If you want to integrate something like dx dy, what do you integrate? You integrate with respect to all these lines, right. That is what you Fibini's theorem tells you. Okay. You write this one as something like integral of with respect to dx and then you with respect to dy, you see. So, you know the same thing I am doing in. So, you surface area you do that one. So, this is equal to integral 0 to 1, you already computed that r power n minus 1 and this is the surface area of ball of radius r equal to B1. Okay, so, that is this is not this is B1. So, now you integrate, this is surface area B1 of 0 into r power n by n, that is equal to 1 over n, that is same as this formula. You see, you have dB1 of 0 equal to n into that one. That is why. Now, let us go to our case. I want to understand this one, integral of 1 by mod x power alpha over B1 of 0 dx. I use that method. This is equal to integral of, so I use the same thing, this is a radial function. So, this is nothing but 1 power r power alpha dr integral of dBr of 0 dsr of y. So, you should know how to do this one, but that is the volume, right, that is the surface area. So, you will have 0 to 1 by r power alpha and this is nothing but this is nothing but r power n minus 1 plus volume 1 dB1 of 0, this is independent of r, that we already computed, into dr. So, this is equal to modulus of dB1 0 integral. So, we reduced it to a one dimensional integration, that is what we have done, since it is a radial function alpha minus n plus 1 and this is one dimensional and this is finite if and only if alpha minus n plus 1 is less than 1 or if and only if alpha less than 1. So, this type of singularities integral of 1 by mod x power alpha dx is finite alpha less than n, alpha less than n. Now, look at here. So, this is an exercise I am giving you. You have to do these exercises. Phi x you already know it. So, look at phi x. Phi x is behaves like 1 by mod x power n minus 2, right, if n greater than 3 equal to 3, n equal to 2 it is log mod x, right, log mod x. This is locally integrable by this reason. For n equal to 2 you can do it separately locally. Now, you compute d phi by dxi, d phi by dxi, you can see that this behaves like 1 by mod x power n minus 1, again implies locally integrable. These are some exercises, but you try to compute d square phi by dxi xj, you can see that this behaves like 1 by, you just miss it. When alpha equal to n, it is not locally integrable. You have to see that alpha equal to n, 1 by mod x power n is not locally integrable. Okay. So, this is not locally integrable. So, you cannot do what we were doing there, integrable. So, this is the difficulty, you will see the effect of. So, you are just missing the local integrability. If something like 1 by mod x power n minus epsilon, then it will be locally integrable. So, you just Laplacian when you take like a second derivative, you miss by any small number, okay. And you will see this effect of this when you study the Newtonian potential, perhaps not now, maybe in the second course, and leading to the introduction of some Heller spaces. Okay. So, this is a small singularity which creates trouble when you take the thing, which at the same time it stores some information, okay, and that prevents you from taking integral under the integral sign, and it contributes something. So, we are trying to understand its contribution, what this singularity contributes. So, we will do this. Okay. So, we will, so please do these exercises. It is important that second derivative just misses local integrability. So, let us now try to do some results. Being studied this much, let us try to do some case, some interesting thing. So, we have your so recall now. So, this is the trouble. Recall u x equal to integral phi of x minus y f of y dy. This is not that bad, only thing you are not able to take the derivative 2 times derivative inside. This is locally integrable, now you know that. So, you are doing this Rn. So, I want to give you the meaning, Rn locally integrable. Okay. I do not want any trouble from f. So, assume f is a continuous function. So, that has no singularity, and also there is the trouble can come from infinity. So, for which I will use CC, that is compact support. Compact support. Compact support means if you have something f is 0 outside a ball, outside a ball or a compact set, whatever it is. So, f is 0 outside a compact set. So, at infinity there is no trouble, and phi is smooth outside, throughout smooth. So, phi is entirely smooth, it has only singularity. So, the only trouble is local, and we already seen that f is locally integrable. So, this u is well defined, that is what I want to say. With this assumption of f is CC of Rn, and by our proof that f is locally integrable, the f has no singularity, So, phi of x minus y f of y dy, f of y has no singularity. So, in any finite compact domain there is no issue, and then outside f is 0. So, the u is well defined. Okay. So, the only problem is because of the singularity you may not be able to take the derivative. Again there won't be a problem to take one derivative. The issue is that when you want to take two derivatives, because then d square phi by dxi dxj will come into picture, which is not locally integrable and it won't be meaningful. So, we want to get rid of that. So, okay. So, we will assume f is in C2. So, we are going to do something, or C infinity you are assuming. So, ux by a change of variable, ux can also write it as you put x minus y equal to t. So, you can also write it as phi of y f of x minus y. This is a very nice thing about convolution. Convolution has very interesting property. Okay. So, you already seen that this is equal to phi star of f, this is also phi star of f. Okay. So, you can take, because of the translation invariance of the measure, you can put x minus y equal to t and arrive that one. So, now you see why did I use this expression, but look at now if I take a derivative of u, the derivative goes on f, not on phi. Okay. So, I can immediately do some thing, I can immediately, so these small exercises you can do that one. Okay. Because now I can take these are all you can justify using theorems from Lebesgue integration or whatever it is, because once you take a derivative you have to justify. So, you understand now you are taking derivative with respect to x and phi x is not coming. So, I do not differentiate now phi because it is with respect to y. So, I differentiate with respect to x. You can prove this actually. I can do as much as possible as long as f has my derivative. That means I can write this is phi star of. So, I have to differentiate. This is again a special property of my thing, you see. In fact, I can do the next I can do a second derivative dx u by dxi xj is equal to integral of phi of y d square f by dxi dxj. So, you see I am not touching my phi which has a singularity. So, as long as my f has differentiability I can go on doing this. So, this is nothing but phi star of d square f by dxi dxj. Now, we have assumed only f is C2, twice differentiability and compact support. In particular, if I take I equal to j and sum it, in particular we get Laplacian of u equal to phi star of Laplace. I could write now this way, you see this is a nice formula. Okay. Earlier we were trying to write Laplacian of phi star f, that was wrong because phi you cannot make assumptions, phi is given as a fundamental solution. So, I started with an f which is nice, that means it is twice differentiable and which has a compact support. So, my convolution is well defined and I could put my derivatives in the other thing, and this is a general thing when you have a convolution, and convolution operators are used for many purposes, even to smooth non-smooth functions by taking convol. So, probably when you study more partial differential equations or other subjects, you will come across something, how do you smoothen, because many times you can do analysis only if your function is smooth. So, what you do is that if the function is not smooth, try to approximate by smooth functions, and convolution is very effectively used together with what we call it modifier, which I do not think we will be defining here. If necessary we will define as and when it is required to smoothen this thing, and you see this here. So, one of the function phi need not be smooth, they are singular, but then you can still do the convolution by taking a derivative. Now, we want to understand what is this, that is all we are trying to do. Can you recognize this? Can you do something more? What is this? Okay. Okay. So, what we are going to prove a very interesting theorem. So, let me write a theorem now. Okay. Let f belongs to, so this is not a boundary value proof, it is a problem in full Rn. Let Cc of 2 of Rn, okay, and phi be the fundamental solution of minus Laplacian. You have to use the same thing. Okay. If you are changing the sign, and some books may use fundamental solution of Laplacian, there will be a sign change, and define u equal to phi star of f, then phi u solves minus Laplacian of u equal to f. You will see that is why we are used that. So, you see it is not Laplacian of u equal to 0. So, it got back your f via this thing. Okay. All right. So, we are going to prove this theorem if maybe in the next class we will try to prove this one, but before that I want to make some, I will prove this, try to prove in the next class. I hope I will be able to complete the proof. So, you see, so it recovers minus Laplacian of u equal to f is actually minus f. This is what you are proving, minus Laplacian of u equal to f. You see. So, let me make a remark before thing. So, we have solved Laplacian of phi equal to 0 in Rn minus 0 in Rn minus 0. So, the question is that, but what is Laplacian of phi in Rn? What is Laplacian of phi in Rn? You cannot do point wise. So, this is the kind of modern or advanced thing in the sense of distribution which we may not do. Maybe we will at the end of the course may not be in this course, maybe in the next course. In the sense of distribution, this is not classical, non-classical. Okay. That is the modern or advanced PDA. This phi satisfies Laplacian of phi minus Laplacian of phi. So, that is why it's all we call it a Dirac delta distribution. What is the meaning of this? What is this? It's nothing like a point wise. So, you take the meaning is take any xi belongs to Cc of Rn, Cc infinity of Rn, then integral what we want to show here, integral of phi of x Laplace, I can take Laplacian psi here, Laplacian of psi of x. This is meaningful because phi is locally integrable. This is not. You cannot take integral of Laplacian of phi because Laplacian of phi is not locally integrable, but I will do this is some sort of an integration is equal to minus psi 0. This is true for all psi in this thing. So, that is how you understand. You see, this is the actually what we are doing is that we are trying to understand this in the proof of theorem, since you do not know what is distribution, and phi has information stored at the singularity, something like this what I explained here. In the sense of distribution, we are trying to understand the action of phi on test functions. That is what integral of phi of x, Laplacian of phi is its action, and that gives you that. And delta naught is called the Dirac delta, is Dirac delta. So, what in the next class I am going to prove to give you the proof of this theorem. Okay. So, I will stop for the time being before starting the proof, because the proof may require some amount of time, and hence I will move to the next class. Thank you.